So in the interest of time, I think everybody got through the first part of it where you're thinking about the formation of the mixed anhydride, right? So our carboxylic acid reacting with ADP, or with ATP, we produce ADP and we form this mixed anhydride. In the next step, it's a fairly straightforward SN2 type reaction where we have our nucleophile nitrogen on the amino acid. It attacks the carbonyl. We form an intermediate, the intermediate collapses, and we release phosphate. Okay, so both of these steps are reasonably straightforward SN2 type chemistry. You have a nucleophile, it attacks a carbonyl, we form an intermediate. We have a nucleophile, we attack a carbonyl, we release phosphate. Okay, what I really want to stress here as a major theme that we're going to see all semester long is why, so not just why ATP is important. ATP is important because its hydrolysis provides the energy to drive this non-spontaneous reaction, but how it works, right? The ATP hydrolysis step occurs in step number 1, right? So it's this step right here where we have ATP reacting with our carboxylic acid. That's the first step. That's where the hydrolysis happens. The really important thing here is recognizing that we form this intermediate which contains a high energy bond. Okay, so hear me out really well here. The hydrolysis of ATP, that energy is stored in this bond, right? That's the important thing here, is we can use ATP hydrolysis to power a non-spontaneous reaction by storing that energy in a covalent bond. And in this case, that covalent bond is in this mixed anhydride. So then in a subsequent step, we can have another nucleophile attack the carbonyl and phosphate's released. And releasing phosphate is very spontaneous. It's breaking a high energy bond. And breaking that high energy bond is the energy that allows the formation of a bond that otherwise wouldn't be able to be made. Right? So this theme we will see over and over and over. Okay? Whenever ATP is involved, or another high energy molecule that powers a reaction, you should not think about hydrolyzing ATP as a separate, distinct step. You should think about it as the first step that creates an intermediate that allows the rest of the process to happen. Okay? That makes sense? Any questions on that? Okay. So I think we finish up with this enzyme DNA ligase. I believe this is the last question on your activity. 6 and 7, yeah, 6 and 7 and 8 all kind of deal with the idea of DNA ligase and kind of some themes with it. Okay, and you probably talked about DNA ligase a little bit with Dr. Hurlbert when you talked about DNA replication, right? So remember on the lagging strand, the Okazaki fragments, we always end up with breaks in the DNA chain. DNA ligase is the enzyme that catalyzes the repair of that break, the repair of that nick in the chain. Okay, so simply said, it creates a phosphodiester bond within a chain of DNA, right? So we have a 3' hydroxyl group, we have a 5' monophosphate, and this 3' hydroxyl is a nucleophile that attacks that phosphate, okay, and ultimately we release hydroxide or water. That's the overall reaction. But this reaction by itself is not spontaneous. Right? Ligase reactions aren't spontaneous. They're not. You're taking two things and making them into one. Entropically not spontaneous. Almost never are they enthalpically spontaneous. Usually they're enthalpically neutral or enthalpically non-spontaneous. Okay? Ligase reactions are not spontaneous. Okay? So the idea here is that we always have to power them with something else. And In this case, we can power them using either ATP hydrolysis, or curiously enough, there's a class of a fairly large class of DNA ligases that can use NADH as a power source. So hydrolysis of NADH. Okay. Today in the activity, we're going to work through thinking about how ATP is used. Okay. In your problem set, you might want to think about how NADH might be used. We won't look at the structure. We'll just kind of. So one thing that I do want to note here is that if you look into the active site, what you'll notice is that there's an AMP molecule covalently bound. So what this means is that during this reaction, ATP is hydrolyzed to AMP. Okay, and we release pyrophosphate. Okay, that's going to be an important part of the reaction. Another interesting thing is we have this AMP phosphoamide intermediate, where the AMP is covalently bound to a lysine side chain in the active site. Okay, and in your activity, the very first step, it shows you that intermediate. It shows you what a phosphoamide looks like. Okay, so you're going to want to think about how that forms, because at the end of the day, that's the first step in DNA ligase reactions. It's the step that hydrolyzes ATP to AMP, and that hydrolysis, the energy of hydrolysis gets captured in the formation of this phosphoamide intermediate. Okay, so the last part of our activity today, which we have a few minutes to work through, is thinking about how this works. Okay, I will have a step-by-step work through of this in the key that's posted. So if we don't finish today, which you probably won't have time to get all the way through, you'll at least be able to see the steps, and I'll make a video of how it works too, so you can hear me talking through it. Okay?